All right, let's take a trip way, way out to the very edge of our solar system. We're going to a place of incredible wonders, a world we actually know very little about. This is a place with giant storms that can appear and vanish in a cosmic heartbeat, winds that scream at nearly supersonic speeds, and a moon that tells a story of a truly violent past. Today, we're diving into Neptune, the most distant and mysterious planet orbiting our sun. But before we get into all its wild features, we have to tackle a really fundamental question. You see, Neptune is the only planet in our solar system that you absolutely cannot see from Earth with the naked eye. So how in the world did we even find it? The story is just fantastic, because it wasn't discovered by someone stumbling upon it with a telescope. Nope, it was found with something far more powerful: pure mathematics. Yeah, you heard that right. This is a cosmic detective story, and it's an amazing testament to the power of physics. Neptune has this really cool claim to fame. It's the only planet that was discovered through mathematical prediction, not by just happening to look in the right place at the right time. So here's how it all went down. Back in 1846, an astronomer in France named Urbain Le Verrier was studying the orbit of Uranus, and he noticed something was off. It was wobbling. It just wasn't moving exactly the way Newton's laws of gravity said it should. So he came up with a bold hypothesis. There must be another hidden planet, even further out, and its gravity was tugging on Uranus. So he hit the books, did all the math, and calculated exactly where in the sky this mystery planet had to be. And the power of that prediction was proven almost instantly. It's actually incredible. Le Verrier sent his calculations to an observatory. An astronomer named Johann Galle pointed his telescope to that exact spot in the sky, and bam, he found Neptune in less than an hour. It was almost precisely where the math said it would be. Just amazing. So for more than 100 years after that, Neptune was just this tiny, faint blue dot. Its secrets were locked away, billions of kilometers across space. But that all changed, thanks to this once-in-a-lifetime alignment of the planets that allowed one single heroic spacecraft to finally pay a visit. And that craft, of course, was Voyager 2. After launching way back in 1977 and swinging by Jupiter, Saturn, and Uranus, it began its final 3-year sprint out to Neptune. This was it. This was the grand finale of its legendary grand tour of the outer solar system. And in 1989, for the first time ever, humanity got a real close-up look. And this quote from one of the NASA analysts at the time just perfectly captures the feeling. Can you even imagine being in that control room, watching that fuzzy blue dot slowly transform into a living, breathing world with clouds and storms and rings, things nobody had ever seen before? The feeling in that room must have been absolutely electric. And you know what? That excitement was completely justified, because what Voyager 2 found was a total shock. This cold, distant world billions of miles from the sun wasn't some quiet, serene ball of ice. Oh no, it was the most violent, storm-tossed planet in the entire solar system. The numbers that came back were just staggering. Voyager clocked winds on Neptune screaming at 2,160 kilometers per hour. To put that in perspective, that's almost supersonic. These are, by a long shot, the fastest winds ever recorded on any planet, period. And this created a real puzzle. You see, Neptune's sister planet, Uranus, is pretty similar in size and what it's made of, but its atmosphere is, well, it's kind of boring and calm. So why is Neptune so incredibly stormy? Well, the answer seems to be deep inside. Unlike Uranus, which is weirdly cold, Neptune radiates more than twice the energy it gets from the sun. It has this powerful internal engine that's churning away, and that's what's likely driving this absolutely ferocious weather. Now, the most famous thing Voyager saw was this massive hurricane the size of Earth that they called the Great Dark Spot. But here's the crazy part. When the Hubble Space Telescope took a look just a few years later, it was gone, vanished. And we've learned since then that this is just what Neptune does. These giant storms are fleeting. They pop up, drift around for a few years, and then just fade away. It's a huge contrast to Jupiter's Great Red Spot, which has been raging for hundreds of years. But the incredible discoveries didn't stop at the planet. Voyager 2 also gave us our very first look at Neptune's biggest moon, Triton. And it became obvious, really fast, that Triton is no ordinary moon. It's an imposter. It's a captured world, a refugee from the solar system's frozen frontier. The key clue to Triton's weirdness is its orbit. It circles Neptune backwards, in the opposite direction that Neptune spins. Literally no other large moon in the entire solar system does this. And that's the smoking gun. It's the absolute proof that Triton didn't form alongside Neptune like our moon did with Earth. It came from somewhere else and got snagged by Neptune's gravity. So the leading theory is basically a story of cosmic drama. Triton probably formed way out in the Kuiper Belt, that big ring of icy bodies where Pluto lives. And it likely wasn't alone. It was probably part of a pair, two objects orbiting each other. But when this pair wandered too close to Neptune, the giant planet's gravity ripped them apart. Triton got captured into orbit, and its poor partner was violently thrown out into deep space. And this captured world is just spectacular. For one thing, it's bigger than Pluto, which means it was probably once the king of the Kuiper Belt. Its surface has almost no craters, which tells us it's geologically active. It's constantly repaving itself with active cryovolcanoes that spew out plumes of ice and nitrogen. All this activity strongly suggests there could even be a liquid water ocean hidden deep beneath that icy crust. So that single flyby from Voyager 2 completely changed our understanding of Neptune. But like any good exploration, it also opened up a whole new set of questions. And in the decades since, powerful telescopes like Hubble and now the James Webb Space Telescope have only deepened the mystery, revealing that Neptune is even stranger than we could have imagined. And this has led to some really recent, really baffling discoveries. When the James Webb Space Telescope took Neptune's temperature, it found that its upper atmosphere has gotten dramatically colder since Voyager's visit back in '89. Why? We have absolutely no idea. It's a brand new mystery for a planet that's already full of them. And honestly, the list of puzzles just goes on. Its faint rings have these strange, clumpy arcs that by all rights shouldn't be stable, but they are. We still don't have a solid explanation for where all its internal heat is coming from. Oh, and its magnetic field is totally bizarre. It's tilted by almost 50 degrees, and it's way off center from the planet's core. It seems like every time we look at Neptune, we just find more questions. So after one brief, tantalizing visit and decades of just staring from afar, we're left with so many more questions than answers. And sadly, there are no confirmed missions plans to go back to this distant, deep blue world. It's a planet that clearly has so many more stories to tell, which just leaves you wondering, who's going to be there to finally hear them?
Welcome to the debate. Today we're focusing on one of the great mysteries of our solar system, the extraordinary atmospheric dynamics of the ice giant Neptune. This is a world where, equatorial winds tear across the surface at speeds of, 2,160 kilometers per hour. And storms, like the famed Great Dark Spot, have been clocked at an astounding 2,400 kilometers per hour. To put that into perspective, that is the strongest wind speed ever recorded on any planet in our solar system. So this extreme dynamism, it really begs a fundamental question. What is the primary energy source powering all this meteorological violence? Is the main engine behind Neptune's uniquely fierce weather its own intrinsic higher internal heat, or are external factors, specifically these seasonal solar interactions, the dominant kinetic mechanism? I'll be contending that Neptune's internal energy is the fundamental primary driver of its extreme atmosphere, while my colleague...
I'll be contending that Neptune's internal energy is the fundamental primary driver of its extreme atmosphere, while my colleague... Actually, highly significant solar and seasonal external forcing is the critical factor, the one dictating the planet's visible atmospheric dynamics and, importantly, the cyclical nature of its most notable storms.
Okay, so my position, it really begins with a crucial comparative analysis. We have to look at Neptune's nearest relative, the other ice giant, Uranus. They're often called planetary twins, similar size, mass, composition, you know the deal. Yet the difference in their atmospheric activity it's absolutely staggering. Neptune possesses this robust internal energy source. It radiates approximately 2.6 times more heat out into space than it actually absorbs from the sun. This means Neptune has a kind of high-powered, constant internal furnace running deep inside. Now, in stark contrast, Uranus, it radiates hardly any excess heat at all. It's almost in equilibrium. So that thermodynamic engine on Neptune, I argue, directly generates and maintains the massive kinetic energy required for winds that are, nearly supersonic. Uranus, lacking this internal furnace, has comparatively sluggish winds, reaching only about 900 kilometers per hour. To me, this evidence is pretty conclusive. Solar input alone, which is nearly identical for both planets, simply isn't sufficient to explain the extremes we observe on Neptune. That difference, that massive disparity in energy, it has to be volumetric and intrinsic. Something else is at play there.
Right. I understand the appeal of the Uranus comparison. It seems mathematically tidy. I get that. But I think it might distract us from the crucial atmospheric instability we actually observe on Neptune itself. So while internal heat, okay, maybe it sets a very high baseline for the overall atmospheric kinetic energy, the necessary raw power perhaps. The observable seasonal effects driven by solar input are, I believe, the critical mechanisms. They modulate, organize, and visibly drive the dynamic systems we actually see. Look, Neptune has a 28-degree axial tilt, right? Very similar to Earth and Mars. Because of its massive 165-year orbit, this tilt means Neptune experiences seasons that stretch out over an enormous 40 Earth years each. Now, you're correct. The sun is incredibly dim out there, providing only about, 1,000th the light Earth receives. It's minuscule. Yet these seasonal changes are surprisingly and measurably impactful. For instance, we've actually documented that during the southern hemisphere's spring, there's a warming of about 10 degrees Celsius in the atmosphere. Okay, 10 degrees isn't huge, but listen. This modest warming causes a critical atmospheric effect. It releases frozen methane from the lower atmosphere, the troposphere, up into the stratosphere, and this causes that high-altitude region to appear visibly brighter. So, this measurable shift in the phase and distribution of atmospheric components, it clearly demonstrates that even minimal external sunlight has the power to drastically alter the thermal and chemical characteristics of the upper atmosphere. This external forcing acts as the critical switch, I think, that dictates where, when, and how the turbulent weather manifests.
I appreciate the detailed discussion of the seasonal changes, but let me offer a different perspective here, especially when we think about the underlying energy budget. If solar forcing, this tiny, tiny sliver of light, were truly the primary dynamic driver, shouldn't that 10-degree seasonal shift create relatively similar atmospheric behavior across both ice giants? Adjusted maybe for minor compositional differences, perhaps. But again, we come back to the scale. Uranus, the structural twin, has maximum wind speeds less than half of Neptune's. To generate a 2,400 kilometer per hour storm, that requires an immense, constant, foundational energy supply. The accepted scientific explanation for this disparity isn't just compositional tweaks. It's that Neptune either captured its excess heat during formation, or, maybe more compellingly, it avoided a catastrophic impact that poor Uranus might have suffered. This allowed Neptune to retain significantly more primordial heat, and that retained energy, that internal furnace, is what fundamentally powers those extreme winds. The difference, I maintain, is the intrinsic engine, not the minimal extrinsic flicker of the distant sun.
Well, you rely pretty heavily on that internal energy differential, but that assumes the two planets are otherwise perfectly identical, which is, let's be honest, a major extrapolation when you're considering the complex fluid dynamics of gas giants. But okay, let's step away from Uranus for just a moment and look at the lifespan of the features on Neptune itself. This is where the internal heat argument kind of falters for me. Remember Voyager 2? It observed the massive Great Dark Spot, the storm with those 2,400 km/h winds, back in 1989. It was spectacular, right? A clearly defined feature. However, when the Hubble Space Telescope checked back on Neptune just a decade later, in 1999, poof! That colossal storm had completely disappeared. And other major storms, we've seen them appear and vanish cyclically since then. Right. This transience is key. Think about Jupiter's Great Red Spot. At least 350 years, maybe longer? Precisely because it is maintained by that steady, intrinsic energy source. So, if Neptune's atmospheric dynamism were dominantly fueled by a constant internal heat source, why would its largest, most energetic features dissipate so quickly? It just doesn't quite add up.
This volatility strongly suggests the weather systems are highly sensitive to fluctuating atmospheric conditions that are far more likely influenced by the 40-year seasonal cycles. These cycles cause them to diminish once the localized conditions, which I argue are dictated by solar modulation, are no longer favorable.
Okay, but I think we need to differentiate between let's call it the baseline kinetic energy of the entire atmosphere and the visible transient surface phenomena like a specific storm. I'm just not convinced that the rapid dissipation of specific vortices undermines the fundamental need for a volumetric heat source to drive the entire planet's circulation at such high speeds. Let's stick with the energy scales for a second. You highlight the 10 degrees Celsius seasonal increase. Okay, fine, that's measurable. But the average temperature of that atmosphere is still around minus 201 degrees Celsius. It's incredibly cold enough to freeze nitrogen instantly. And that baseline kinetic energy, those constant 2,160 kilometer per hour equatorial winds, they are constant. They don't just switch off when a dark spot disappears. It's simply, it's hard to believe that tiny sliver of sunlight, 30 times weaker than what Jupiter gets, let alone Earth, could be the primary power switch for the strongest, persistent winds in the entire solar system. Internal heat rising from the core is a massive volumetric energy transfer. It affects the entire depth of the atmosphere. Solar energy, by contrast, really only penetrates the outer layers effectively. We require that deeper, intrinsic energy to maintain the immense speed and rotation of the planet's atmosphere as a whole, even if the specific surface structures, the storms, come and go. The heat is the constant engine. The solar changes might just be noise on the surface, dictating where the waves break, perhaps.
Maybe think about it this way. I'm focusing less on the bulk kinetic energy and more on the differential energy transfer. The data we have suggests these great dark spots, these massive vortices, they tend to appear where atmospheric bands traveling at significantly different speeds actually meet. So the initiation and decay of the storms seem to rely entirely on the existence and, crucially, the modulation of these specific speed differentials. So yes, internal heat might set that high baseline speed for the atmosphere overall, I can concede that. But external solar radiation is, I think, the key driver of the differential heating and cooling that modulates the flow of hydrogen and, importantly, methane. Look again at the methane release. Solar radiation causes a phase change, moving frozen gas into different layers. This alters the density, the opacity, the interaction between the atmospheric bands. The sun is essentially tweaking the brakes and the accelerator on those different bands. It controls the localized energy and stability needed to initiate a massive vortex. Without that external trigger altering the composition and structure of the upper atmosphere, even if the overall baseline speed is very high, the large spectacular storms we see simply cannot form or persist in the same way.
But doesn't the sheer ferocity, the sheer violence of the movement argue against mere surface modulation? Those storms aren't just shallow disturbances. They must involve deep convection, deep circulation cells. If solar energy is merely a trigger, as you suggest, why is Neptune so much more energetic than Uranus, which receives essentially the same trigger? It always comes back to the fact that Neptune has the available energy, the intrinsic power to amplify that trigger into a 2,400 kilometer per hour monster. If Uranus got the exact same solar trigger, the physics suggest it could only produce maybe a 900 kilometer per hour storm, because that's all the internal energy it has available to tap into. Neptune's internal furnace is the necessary precondition, the amplifier for that extreme outcome.
Okay, I accept that the intrinsic heat provides the necessary preconditions and, yes, the potential for high speeds. However, the transient nature of the storms strongly suggests that that potential is rarely realized on the grandest scale without some kind of extrinsic assistance. If the internal heat were truly the dominant mechanism, the thing actually driving the formation and location, we should see permanence, like on Jupiter. The difference is likely in the materials, too. Neptune's atmosphere contains much higher proportions of volatiles ices like methane and ammonia, which are highly susceptible to phase change even with minimal temperature shifts. This could make Neptune's atmosphere uniquely sensitive to solar input compared to Jupiter or even possibly Uranus, despite the similar solar flux. It might be a highly tuned system where small external inputs yield disproportionately large dynamic results because of its composition.
But this is precisely why we must focus on the persistent movement. The storms disappear, yes, but the underlying jet streams, that 2,000 km/h current near the equator, they never do. That constant, massive movement requires a steady, continuous source of kinetic energy injection throughout the vast volume of the atmosphere, something only Neptune's intrinsic heat budget seems capable of providing on that scale.
And yet, it still seems to be the external cyclical influence that dictates when and where that massive kinetic energy manifests into the spectacular visible features we associate with Neptune's dynamism. The sun appears to dictate the location and the cyclical nature of the visible turbulence, even if the deep engine provides the power.
Well, this discussion really highlights the profound complexity of Neptune, and I suppose where our fundamental disagreement lies. We certainly agree that the weather is dynamically extreme, no question there. But for me, the overwhelming disparity in constant wind speeds between Neptune and its sister ice giant, Uranus, remains the most persuasive and foundational piece of evidence. Neptune's higher internal heat acts as the fundamental power source. It generates the required baseline energy for these violent atmospheric processes. The 2,400 km/h storm winds, they simply demand an intrinsic engine of that magnitude.
And I believe we have to synthesize the evidence. We have the measurable seasonal warming, that 10-degree differential, and the visible methane modulation, and we have the clear transience and cyclical nature of the great storms. These observations taken together demonstrate that external solar input, even way out there at such a vast distance, acts as the crucial triggering mechanism. It modulates the movement of atmospheric components and dictates the appearance and disappearance of the most violent features. So, understanding Neptune really requires appreciating the critical interplay between both the intrinsic heat that provides the raw power and the slow, powerful extrinsic seasonal forcing that seems to act as the switch, determining how that power is expressed visually.
It's important to remember, though, we've only actually observed one full Neptunian year since its discovery in the 1840s, and only one spacecraft, Voyager 2, has ever visited up close.
Exactly. There is still so much we need to learn about its internal structure, its deep atmosphere, and its relationship with external forcing. Considering multiple competing perspectives like ours today, well, hopefully it helps sharpen our understanding, or at least highlights the key questions we still need to answer about this distant, vibrant world.